Now let's look at another important concept, which is known as diagonalizability of a matrix. So a matrix, again, which is a square matrix, is diagonalizable if it is similar to a diagonal matrix, which is given by, actually, use a notation, lambda, capital lambda. Okay, if a matrix A is similar to a diagonal matrix, then it is said to be diagonalizable. So, and under what conditions we can say that a matrix is diagonalizable? So with respect to that we have a theorem. If a matrix is diagonalizable, if and only if it has n linearly independent eigenvectors. So the eigenvectors are linearly independent, which means that the matrix is diagonalizable. It is an if and only if condition, which means if the matrix is diagonalizable, then it has linearly independent eigenvalues, and if it has linearly independent eigenvalues, it is diagonalizable. So there is both an if part and an else part. So if part and only if part, you have to prove both. This is an if and only if condition. So let's take the if part first. So we know that there are n linearly independent eigenvectors, right? And A is diagonalizable. So we are taking x1, x2, etc., xn be the eigenvectors. Okay. So what we do is we stack up all these eigenvectors as columns along a matrix, and we form a matrix S. Right? After forming this matrix, we know A into x1 is equal to lambda1 into x1, where lambda1 and x1 are the eigenvalue pairs. Similarly, A into x2 is lambda2 into x2. So A into S being the eigenvectors stacked together as a matrix. So A into S is actually A into x1, A into x2, etc. into xn. But A into x1 is actually lambda1 into x1. So that's lambda2 into x1. So this one, we can A into S can be formed as, you take the lambdas as a lambdas as a diagonal matrix. This can be written as x1, x2, etc., xn into the diagonal matrix where the diagonal elements are the eigenvectors, sorry, the eigenvalues, and this is A into S. So to find A, we can take multiply by S inverse. So this will be S into a diagonal matrix sigma into S inverse. Right? So S inverse AS is equal to no, we are actually left multiplying by S inverse. So S inverse into S will be equal to the identity matrix. Hence, this will be equal to the diagonal matrix. So here, S inverse AS is equal to a diagonal matrix, which implies which is similar to a diagonal matrix, and hence it is diagonalizable. A is diagonalizable. So this is the if part. Okay, let's once again see how the proof has been done. To prove this, what we have done is we've stacked all the eigenvectors as a matrix S, right? Then we find A into S, which indeed is A into S is S into sigma. A into S is equal to S into sigma. So if you write S inverse AS, that is equal to S inverse S into sigma is equal to not sigma, lambda, which in turn proves that A is similar to this diagonal matrix lambda, where the diagonal elements being the eigenvalues. Now we have to prove the Olive part. So Olive part, what does it say? If the matrix is diagonalizable, then its eigenvectors are linearly independent. Fine. So what we're given is S inverse A is equal to lambda. Right now we have to prove that A has linearly independent eigenvectors. So in a similar fashion, S inverse A is equal to A into S implies A into S is equal to S into lambda, where we have left multiplied by S inverse. Okay, this is S inverse AS is equal to S into lambda. So what does this mean? This is actually similar to the eigenvalue equation which we have, that is A into X is equal to lambda into X, but slightly similar. What it means is A into ith column of S is actually the ith diagonal element of lambda, capital lambda into ith column of S. So this is, which means that ith column of S is an eigenvector of A and its corresponding eigenvalue is the ith diagonal element. So these this form an eigenvalue pair. So but we know that S inverse exists, right? So S inverse exists means all the columns are actually linearly independent. Otherwise, S inverse will not exist. So all the eigenvectors of A are linearly independent. This proof is actually okay. This is how we prove the only if part. So it's we have proved the if part. We've proved the only if part. So what does that say? If a matrix A is diagonalizable, if and only if its eigenvectors are linearly independent. This is for a square matrix C n cross n. And there's a corollary to this. We've already seen that if A has n distinct eigenvalues, it has okay. There's this corollary. What it says is, if A has n distinct eigenvalues, then A is diagonalizable. So the proof is also simple. We've already proved in an earlier lecture that if there are n distinct eigenvalues, then the eigenvectors, there are n distinct, no, there are n linearly independent eigenvectors. So once we prove that, from there, we've already proved that if the n eigenvectors are linearly independent, then it's diagonalizable. So the proof, sketch of the proof is first prove that there are n distinct eigenvalues, then the n eigenvectors are linearly independent. From there, we can prove that it's diagonalizable. So that is a corollary. Okay, let's end this discussion.